All right, so welcome to our next topic. We're going to start talking about probability. This section is going to go a little more in depth because probability is a subject a lot of students struggle with. So the way I always phrase this is the book is called Introduction to Probability of Statistics. We know what statistics are, but what is probability? Probability is basically just counting. It's a proportion of desired outcomes given unlimited trials. It allows us to derive the likelihood of certain outcomes, which basically builds to inference, which is one of the foundation cornerstones of this class. So, with the some of the terms we're going to need to know to talk about probability are experiment, which is the process by which observation outcomes are collected. This is the probability, the way the event is constructed and observed. An outcome is the result of a single repetition of an experiment. This is called a simple event in your book. An event is a collection of outcomes, and a sample space is an exhaustive list of outcomes. Now, can events and outcomes be mutually exclusive? The answer is outcomes must be. That's how we can distinguish between outcomes to experiments. Events can be, but they do not have to be. So let's talk about this in theory. Now, if an experiment is rolling a six-sided die, what's an example of an outcome? Well, we roll one six-sided die. We know that the outcome is basically any number between 1 and 6. Right? Those are the outcomes when you roll a die. And those are mutually exclusive, right? If you roll a 1, that means you didn't roll a 2, 3, 4, 5, or 6, and so on and so forth. An event would be any collection of outcomes. For example, you could say a even number. You roll the same number twice in a row. Or you roll a number that's greater than 7. Just because it's impossible doesn't mean it's not theoretically a potential event. It just means the probability is very, very low. Now the sample space, which is denoted in curly Q brackets, is simply the list of all the possible outcomes. So it's 1, 2, 3, 4, 5, 6. Those are all the possible outcomes when you roll a six-sided die. Now, as we said, any outcome is mutually exclusive to another. So let's talk about events because it's a little more interesting. Mutually exclusive events could be rolling an even number, roll an odd number, roll a number less than or equal to 3, roll a number greater than or equal to 4. These are mutually exclusive. You can only be in one category or the other. So things like that. Now, in theory, probability will always cover two concepts: desired outcomes, which we'll call successes, and non-desired outcomes, which mean failures. Now, it's very important to note that desired doesn't mean good by definition. It just means it's the outcome we're studying, the one we are checking to see whether or not it'll occur. Successes and failures are, by definition, exhaustive mutually exclusive. If you can either be successful or a failure. You can't. If you're a success, it means you can't be a failure. If you're a failure, it means you can't be a success. And either a success or a failure are the only two options. Anything that's not a success is then, by definition, a failure. So this means we can generate some pretty cool rules about probability. Cool, of course, to guys who are big into probability. Now, if P of X is the probability of some experiment X in sample space S, we know that the probability of the sample space can only be 1. You have a 100% chance of an event within all possible events occurring. If it's not 100%, that means there's an event that can occur that's not in the sample space, which means it's not the sample space. Now we know that probability of X must lie between 0 and 1, and the lowest chance something can have of occurring is 0%, and the highest chance is 100%. So we know that the probability of sample space is equal to 1, and that X must be between 0 and 1. So this gives us three types of probability. Subjective probability, and this is the probability when somebody draws on personal knowledge or experience, and it's basically just a guess at how likely an event is to occur between 0 and 1, or 0 to 100%. For example, a student may believe they have a 60% chance of passing a class, right? In the 70s, scientists believe there's a 50% chance that whales would go extinct. So subjective probability doesn't have a lot of good mathematical backing, but it is still important for some concepts. And it's basically used, in general, when people talk about the probability of an event happening, they're drawing on subjective probability. The probability of sports teams winning, the probability of rain, things like that. A lot of times, subjective probability is commonly used. Now, experimental probability is also known as empirical probability, and it's a science probability based on observations recorded experimentally. It uses the relative frequency. You just say the number of times an event occurred divided by the number of observations. So suppose we look at an employee's record, and 49 Fridays he's been scheduled for, he's called in sick for 28. His relative frequency of Friday absences is 28 out of 49, so experimentally we'd say the probability he's going to call in sick next Friday is 57%. Now, theoretical probability is the classical approach, and this requires a good understanding of the sample space. Probability under this model is simply the number of possible outcomes divided by the total number of outcomes. So, if we have enough repetitions, we can see that experimental probability will converge to the theoretical probability. And this is mostly theoretical math that you don't need to be worried too much about for class. Now, this is an important result because theoretical probability might be hard to figure out on its own. So let's think about a coin toss, right? Suppose I flip a coin. I'm flipping a coin right now. And I get a heads, I get a tails, I get a heads, a tails, I get a tails, I get a tails. So now let's think about this next thing. Subjectively, right? Some of you might be thinking heads is due. And so you'd assign a high probability to heads. Like maybe you'll say it's 100% or 70%, whatever. Some of you might be thinking, oh, the coin's off, right? So more likely tails, whatever. But this is just based on basically just guesses, right? It's not based on any evidence. It's based on sort of an understanding. And the human brain, as I've said before, is not very good at understanding probability. Experimentally, right, we have seen that of the last 6 tosses, 2 have been heads. So we have a 2 out of 6, or 33%, 0.33 chance of it being heads. Tails has been 4 out of 6, which means a 67% or 0.66, going on forever. So that's experimentally. But theoretically, right, we know that heads, there is 1 occurrence of heads out of a possible 2 outcomes. And for tails, there is 1 occurrence of tails out of a possible 2 outcomes. So we could say theoretically the probability is 50% heads, 50% tails. So that's basically how we'd break down this example into the 3 kinds of probability.